Hello and welcome to today's SIGMASOFT webinar. Today the topic is going to be a simulation setup demo. So we are going to focus today on bringing models into SIGMASOFT and showing the ease of setup. And this is something a lot of people have asked about. We've done some introductory presentations. And really today what we want to focus on is actually showing the software. So what we're going to do today is take some CAD models into the software. I'm going to show how to build some basic geometry like runner systems and gates, and then show the ease of meshing, and then we'll even go through the setup process and even look at a little bit of results. So my name and information is there at the bottom of the screen, and so I'm Fred Phillips, and I'm going to go ahead and get started here today. So right now we have all the lines on mute, so we'll go through the demo, and then at the end we'll take questions. Okay, so first thing I'm going to do here is I'm just going to open up the SIGMASOFT software. Okay, so as with any software, so right now we have the option to either open an existing project or start a new project. So of course what I'm going to do today is I'm just going to go ahead and create a new project. Okay, so once I do that, it comes up with a couple options. So I have the option here to pick what type of analysis I want to do. So we can either do an elastomer simulation, a plastic, which refers to thermoplastics, or a thermoset simulation, or any combination of those, which would be our multi-component mode. So for example, if you wanted to, say, do a two-shot molding with a thermoplastic that's overmolded by an elastomer, we would pick our multi-component mode. So I'm going to go ahead and select our thermoplastic, and go ahead and just name the project. I'll just name it, say, Test 1. And then here we have the option, if we actually have some sort of a master template, we can use that. But for today's purposes, I'm just going to go ahead and use an empty project and start from scratch. And then we can also select a different directory structure, which all of our files can be saved within. We typically recommend the Sigma structure, especially for customers. That way, if you have any type of technical support questions or issues, when you call our support line, we can easily find those files. So we typically recommend we just stay with the standard Sigma structure. Go ahead and say OK. Okay, so right now we just have a blank interface. So right now I would typically start with the preprocessor, but I can go across the top here and just quickly explain what these different options are. And this really is your workflow. So the preprocessor is where we're going to do any of our geometry importing, modeling, creation, preparing our models in terms of putting a feed system on and mold plates and so forth. So everything geometry-wise to prepare that model for simulation. And then once we're ready for that, then we go into our meshing. So we have what's called enmeshment. This is where we would take all that geometry in and then break it down into points of calculation. So really that's what a mesh is just taking that 3D geometry and putting a mesh through the model to create a bunch of points of calculation. And then our definitions is where we'll set up our entire process. So defining what our materials are, our polymer, our mold steels, our coolant materials, and then also our entire process setup. So your filling profile, your packing profile, cooling times, mold open times, cooling temperatures and so forth. And simulation is where we'll actually run the simulation. Post-processor is the results. So looking at all the results from the analysis. And then we have our database, which includes all of our polymer materials and our metals and steels and coolants and so forth. Then even Composer, which is the tool for actually creating reports to send to people. So we also have what's called a free viewer, a Sigma viewer on our website. So if you're a SIGMASOFT user, you can use Composer to create some files that you can send to somebody that doesn't have SIGMASOFT, and they can download the free viewer and view those within the Sigma viewer. So I'm going to go ahead and go into the preprocessor here and start. Okay, so we just have a blank project right now. And as you can see on the screen, we just have our coordinate system that automatically comes up. And over here on the left side is really where all of our geometry material assignments will occur. So for today's purposes, I'll use a combination of the icons and drop-down menus. I'll try to use as many drop-down menus as possible so you can get it, so that way you can kind of see what I'm doing. I know it's hard if I click icons too much and you not exactly see what I'm doing. So first thing I'm going to do here is just import some geometry. So I'm going to import a CAD model. I can also import some sort of other finite element mesh from other packages. So here we're going to the CAD import. And then first thing here is I'm just going to go to my some models. Then we have, in terms of importing, we can actually bring in SAT files, STL files, STEP files, ProE native files, CATIA native files. So here I'm going to bring in this SAT file. Go ahead and take a look at this part. So what we have on the screen here is a part that's it's not too complex. So we basically have a housing here, a box housing. It has some ribs on it, a boss, a gusset there. I'm going to go ahead and change the color here under that bright red so it can be a little intense. So let me do that. That's a little better. Okay, so here's the part that we're going to look at here first. Spin this around so you can see it. Okay, so what I like to do usually is name my geometry as it comes in. All right, so the first thing I want to do here is I'm going to highlight modeling in a simple runner system. So if you had that runner system in your CAD package, you could bring that geometry in as well. But for right now, what I'm going to do is I'm actually just going to model this. So up here I have a bunch of geometry tools. So we have different rectangles and circles, cylinders, extrusion. We can do sweeping and revolution type capabilities. But for right now, I'm going to use the cylinder command. And really, it's just a start point, end point type situation. So what I can do is I can even click on the part. Just say, okay, I want a gate maybe opposite this rib right there. And then I can go in here and just leave those values or modify them. In this case, I know the center of my part in the X direction, which is our red axis, is 65. Then I'm just going to say round this off to 15. And then 60, of course, is our Z in the blue. So I've picked that surface, so I'm already at 60, so I want to keep it there. I'm going to go ahead and say 65 and 15 here again. And then maybe we'll make that gate come out 2 millimeters. And then here we'll do, say, 0.5 to a 1 millimeter gate. All right, so just like that, we have a gate right on our part. You can even zoom in here on this. You can see that. Now, if I want to go back here and modify that, all I have to do is double-click that. I can go back in and say, well, maybe I want to make it 5 millimeters. Say OK, and it's really as simple as that. So I'll go back and change this to 62. Okay, so next step here is I'm going to go ahead and do another cylinder, which is going to be my runner. So I'm going to go ahead and click here again. Just click on that surface. See, click my cylinder command here. There we go. So say 65, 15 again. And then here we're going to actually do 65, 15. And let's take that out to 80 millimeters. Let's just keep it a consistent 1 millimeter diameter, or 2 millimeter diameter, 1 millimeter radius. Okay, so just like that, we have our runner. Then I'm going to go ahead and do this one more time for our sprue. So go ahead here again, and let's just say keep it at 65 and 15. And then now, of course, we're at 80. And here we'll do 65 again. And now, of course, in the Y, now what I want to do is I want to go in the negative Y direction. So I'm going to go ahead and put in, say, negative 40. And then we'll keep this at 80. And then we'll go ahead and taper this sprue like such. So now what we have a sprue on the part. If you can see here, we actually, we're right there at that intersection. So I actually want my sprue to come past that like you typically would. Put some sort of a cold slug well at the bottom of that. So I'm going to go ahead back in there and modify that, so go ahead and change this, say, to 18. There we go, so something like that. So very simple capabilities there in terms of modeling the geometry. And then as I mentioned, I always like to go in here and rename these. Go in here, a runner, and my sprue. Okay, so next step. So what we want to do here is go ahead and put an inlet on the part. So for every analysis, we have to actually specify where the polymer is going to enter. And of course, in this case, we want the top of the sprue. So I'm going to go ahead and select this surface here. And here we just need to give it some sort of height. Now this really isn't part of the true geometry. We just need to, usually from 2 to 5 millimeters is sufficient. So I'm just going to say 2. This is also where we can assign our tracer particles. So we talked about in the introductory webinar the ability to assign tracer particles, which show you what's happening behind the melt front. So I typically usually go maybe at 30 or so. So I'm going to go ahead and say 30 tracer particles. You could do 40, 50, or 20. 30 usually gives you a good amount. But you can also specify the distribution of those particles. And since this is a round runner, I'm going to go ahead and say put them in a circular distribution. Okay, so we have our inlet now. All right, so the next step here is we just have to put some sort of mold steel around this. Now, of course, within SIGMASOFT, we can bring in our entire mold base. We can have those mold plates. We can have our A plate, our B plate, our top clamping plate, our ejector plate, and all that, and so forth. But at this stage, what I really want to highlight is, you can do a very simple analysis with really just the part. So in this case, I don't have those plates yet in my design process. So right now, I'm just really trying to get a feel for, is the part manufacturable? Where should I put my gate location? What type of pressures am I looking at with the material that I want to use, with the wall thicknesses and the runner design and so forth? So I'm just going to go ahead and put a block of steel around this. So what I'm going to do here is I'm going to go to a different view. So I can do multiple views here, but I like to use the 4 views Sigma layout, which splits it up like this. So we have our our top, our front, our right side, and then our isometric view. And I'm going to go under here under our cube command and really just draw a box around this. I'm going to specify the 2 points there, and then down here I can actually drag that box like such around the part. And then here, go ahead, I'm just going to maybe round these values off a little bit. So go to say 35, 25. Here we'll go, let's see, 90. And maybe in X direction, let's go to 95. And negative 40. And here we can even go maybe negative 10. See what that looks like. All right, so we'll go ahead and say OK. So now we have a block, basically a block of something around this. We haven't assigned it a steel yet, but all right, now if I go back to my one view, go ahead here and rotate this. All right, so really we just have 2 more steps. So what we need to do here is now, so if you look on the left side, everything right now is assigned as a part material. So we need to specify what all of these really are. So under my materials here, I can go down here and use this drop down. I have an inlet, a runner, a gate, temperature controlled runner, which would be a hot runner, or some sort of runner system that's controlled by temperature, inserts, molds, movable half slides, and so forth. So what I want to do is I want to create a new mold ID. I'm going to take my cube and say that it's going to be a mold. As soon as I do that, now we get more of a transparent view where now we can see what's going on inside there. Then also my gate, so I'm going to create a new gate ID. And I'm actually going to create 2 runner IDs because I have my sprue and my runner. And I could assign these all as the one ID, but at this point, by doing 2 IDs, what I'm allowing myself to do is put these on, assign these as different entities or different layers. So later on in the simulation, I can turn on just the runner or turn on just the sprue if I want to do that. So create 2 of these runner IDs. So I'm going to drag my gate down to the gate option. You can see now that's assigned a gate. My runner, say runner 1, and my sprue is runner ID 2. I can even rename this as my mold. Okay. So now what we can do here is I want to go ahead and rename all of the and reorder these. So if I put so what I want to do is I want to create a situation where I'm going to run a Boolean operation, and all this geometry here is actually going to be cut out of this steel, just like you would in the real world. You can actually have a true cavity through that steel. So what I want to do is specify the way that this flows. So my mold is first because I want to cut everything underneath that out of that mold. Then we have our inlet, our sprue, our runner, and then flow through our gate, and then our part. And then once I get that set, I'm just going to update my booleans. And they'll turn green, so we are ready to go. So next step is our meshing. So you can see that wasn't too hard, and if I wasn't explaining it, I probably could have done that even a lot quicker. So I'm going to go ahead here to my meshing. All right, so here is, there's a couple options here. So we can do an automatic mesh, or we can do a standard or advanced mesh, which allows you to assign some more specific parameters. So for this example, I'm going to highlight the automatic meshing. So here, what I'm going to do is I like to start with a model like this, typically around 2 million elements. Now, 2 million might sound like a lot, but it really is not, because what 2 million really means is it's the entire mold is going to be meshed, the runner, the gate, and the part. So go ahead and say OK, say generate the mesh. You can see it's very fast, so it took maybe 2 seconds. And really what we have here, so we have total control volumes, or total mesh size is just under 2 million, like I specified. And our part cells is really what's important. So this is really what's going to control your computation time. And this is really what we want to pay most attention to, is the amount of part cells that make up or the amount of mesh that makes up the geometry, the part geometry. So here we have 166,000 elements, which is pretty small. This would run very quickly. And so I'm going to go ahead and say finish. Now, in this case, we can see that we have no issues, but I want to look at the mesh and see, okay, well, how fine or how coarse is this mesh? So I'm going to go ahead here and take a look at the mesh. Now, the idea with SIGMASOFT is we recommend that you have 3 elements through all of your thicknesses. So as long as you have 3 elements through the thicknesses, it'll be sufficient for analysis. Okay, so first thing here I'm going to do is I'm going to turn on my meshing. So I'm going to turn on my grid line so you can see that. So here's the mesh that's on the part. So it looks like a very nice clean mesh, and I should point out too that there's no cleanup required. So by using the cuboid mesh type that we use, there's no chance for overlapping elements or aspect ratio issues or anything like that, or connectivity issues. So what we have here is a very nice looking mesh. Now, if I want to go in here and look at it a little closer, I can see that I have 5 elements through the thickness in this area. And I could go into some other areas as well to go through here. I can see I got more elements than I really need. Like I said, 3 is really what I'm aiming for. If I know I have a very high shear sensitive material, I may go for 4 or 5. But at this point, I have 2 options. I can run the analysis just like this, but what I probably can do is put a coarser mesh on this and get as good of results, and it would take less computation time. So you're always finding that balance between mesh density and computation time. So based on this, I think I want to make this a little more coarse and get that element count down just a little bit. Okay, so go back to my meshing wizard now. So instead of 2 million, I'm going to go down to 1 million. Say OK. Now, if there are any areas of the part that don't have 3 elements to a thickness, it will tell me. So the nice thing about this is if I don't see any warnings, I know that I'm good still. So based on this, even when I specified 1 million, now I got my part cells down to 82,000. I still have a pretty good quality mesh. So at this point, what I want to do is I want to see, well, how low can I go? How low can I go until I start having issues? So go down to 900,000. Still, it looks like a good mesh. Take it down to 800,000. Generate. And it's so fast. I mean, you can go through these iterations very quickly. So 800,000, go down to, say, 700,000. Okay, so looks like we've hit that threshold where now between 700,000 and 800,000 elements, we have some issues. So now it's pointing out that I have 134 2-layer elements. So what that means is I have some regions of my part that only have 2 elements through the thickness. So now again, I could continue with this, but based on our guidelines and rules, we want to make sure we have 3 through all of the critical areas or most important areas. So at this point, I know that I can quickly just be done. I can go and say, you know what, 800,000. Gave me a good mesh. Let's just stick with that, and we are good. So at this point, I'm done meshing. So for the entire project, now we're done with the meshing. Now we can move on to the more important things. Looking at our setup, changing different parameters, and looking at results, and going through that iterative process of analysis. So now I'm going to go into my definitions. Now here it's going to ask me the mesh information. Do you want to basically map this to the geometry? So I'm going to say yes. So by clicking that, what happens is it takes that mesh and maps it back to my geometry. So that's why when you're looking at results, you actually do see the true 3D geometry. You don't just see the elements like you saw there when I showed the mesh. Okay, so here, now we're into our definitions. So we have material, heat transfer, process definitions. So the first step here, of course, is going to be my part material. So I'm going to go ahead here and pick what type of polymer I'm going to use. So I'm going to go into my database. So here I can scroll down through many of these different resins here, and maybe in this case, let's pick a DuPont, maybe this DuPont G43. All right, so when I pick that, it comes up with information about the material. So it's a nylon 6/6 semi-crystalline, 43% glass filled. Has information about the testing and how that data was achieved, which is very important inside of SIGMASOFT, is making sure we have good material data that's not generic, not supplemental, but it's been tested data, and our mechanical data is multi-point data as well. and then our mold temperature range, our melt temperature range, and different ejection temperatures and max shear rates and so forth. So here it's giving me my mold temperature suggestion. So 100 is the recommended mold temperature, 295 is my recommended melt temperature, and it puts that 295 in there automatically. So I could go in here and modify that and say, you know what, I want to use 300. Go ahead and say OK. Then I can go under here and say, okay, next is my mold material. So go ahead and select that, and then pick same thing. So now I want to go under here and go down to my mold steels. So here you can see I got lots of different mold steels to pick from. So let me go ahead and pick my, I'm just going to say P20 for this example. Then here 100 was recommended, and I'm just go ahead and leave it at that. Say OK. So now I have my polymer material and my mold steel. Now if I had different mold plates here, if I had some inserts and some core pins and so forth, all of those would be different entities, and I could assign those different materials. So I could say my mold plates are P20 and my insert is H13, or my core is beryllium copper and so forth, and even assign those all those different properties. So the next step here is heat transfer definition. Now in this case, we don't have a lot of different mold components, so this is a pretty simple assignment here where I can go ahead and just assign it. And we give you these recommendations during training. So typically, a heat transfer of 800 between the polymer and the mold is what we recommend. So in this case, I'm just going to pick that. Now, if you had a bunch of different mold steels and different plates touching each other, that's where you can really go in and really start to increase your level of accuracy in terms of saying, this is the heat transfer between these type of different materials. And we have, again, we have some training that kind of describes, the different values that you would use there. But it gives you a lot of control if you want it to really determine proper heat transfer between different materials, especially if you have air gaps or scale in your runner system, or I'm sorry, in your cooling system, and you want to account for that. Maybe the heat transfer through your cooling degrades over time because of scale buildup. And you can adjust that heat transfer to offset that. Okay, so next is our process. So here, just like setting up an injection molding machine, I'm going to go ahead here. First, I'm going to say, okay, what do I want to calculate? So I'm going to calculate my filling, calculate my packing, and then I could also do my external cooling. This is a simulation after the part's ejected we could turn on, or we could do just a thermal-only analysis. So in this case, I'm just going to do filling and packing at this point. And then here's our cycle. So similar to an injection molding machine, here we have any type of service time that needs to be assigned, any type of preparation, so placement of inserts, time, any time during the preparation phase we want to specify. And then once the mold's closed, then any type of delay time before we start filling, specify our filling, our packing. We can determine, any type of sequential valve gating if we want to, open those gates at different times. And then our cooling phase, how long is the mold closed before we open the mold. And then over here, we can specify when to open that mold. So here, now I can go ahead here and I can pick these values on the screen. I can go and select them over here. So there's different options of ways to do it. So I can go ahead here under my fill time and just double-click that. So it comes up with this value here of saying, okay, you can specify either a filling time, or you can specify a flow rate. So flow rate over time, or filling depending on a pressure curve. So for simplicity today, I'm just going to go ahead and specify fill time, say a half second. Then I can go ahead and calculate the tracer particles. I can detect weld lines. And even if I have some sort of pressure limit that I want to specify, so if it reaches this, it'll say, hey, you've reached your pressure limit. We cannot fill this part any further. So once we get our filling assigned, we can go on to our packing. And then same idea. So here we can specify a packing profile by a pressure given or relative to a filling pressure. So here I can go in and say, okay, well, my packing profile is going to be relative to my transfer pressure. So here I'm actually going to switch over, say, at 98%. So I'm going to do velocity control up to 98% and then switch over to pressure control. And then here I can go ahead and specify a profile if I want, or a constant pressure. So I can start here at 0, say, we're going to drop down to 80%, and then let's say let's hold it at 80% of that transfer pressure for, say, 10 seconds. So we'll keep that at 80. And then we can even drop this down to, say, 50%. So just something like that, and then maybe hold that till maybe 5 more seconds, like such. It might take 0.1 second to adjust the machine, and then take that down to 0. So any type of packing profile you want to do, you can go ahead and specify that. Or if you have these values in a text file, or you want to do multiple iterations and save that, you can import that file as well. Let's go ahead and say OK. Then here, go ahead and say calculate tracers during the packing phase as well. And go ahead and say OK. All right, so the next step here is specify our mold closing definition. So basically, how long is our mold, how long does it take before we're going to close that mold during the service and preparation time? So let's say 2 seconds is our mold open time, basically. And then our mold open control actually specifies when the mold actually opens. So how long is our cooling time, basically. So what this does is it includes our packing time. So let's say 30 seconds is going to be our cycle before that mold opens. So it's going to control when the mold opens. Specify OK. Now under here I can go ahead down to my result definitions, and here's where I can specify what time steps I want to output the results. Now there's a default here where it has during the filling phase we're going to output them every 2 seconds. I can go ahead here and say, what, I want to do it every, from 0 to 100 every 1 second. Say insert, say apply. I can even go under time and say I also want to do it in addition to the percent. So I want to do it, say from 0 to our fill time was 0.5. So I want to do it every 0.1 seconds and apply that as well. So I get those definitive time steps as well. And I can do the same thing under my cooling, which includes my packing. So I go say 0 to 100 every 1%. Apply that. Say OK. Now if I had external cooling going on, I could also apply those steps. But over here for this exercise, I'm not going to do any post-molding calculations at this point. Say OK. Then under result options, we can even select different results that we want to appear. So I can get my shear heating, my shear stress, heat flux, cool rate. Say OK. And I can also specify my shrinkage and warpage at this point. I'm going to go ahead and leave that off for now because we're just going to do a filling and packing. And then I'm pretty much ready to run my analysis. So I can go ahead here and say go to simulation, save it. Okay, so under here I can go ahead and specify how many CPUs I want to run this across. So let's just do 2 for right now, since I'm going to multitask here today. And then start the analysis. All right, so we typically get this warning that pops up. So although I assign 30 tracer particles, what it usually does is it looks at the mesh density and the geometry size, and it usually determines something that makes more sense in the particle size. So even though I specified 30, it might look at the number of elements and the volume of the part and say, well, we can only really fit 28 tracer particles or 26 or something like that. So this warning usually pops up saying, hey, we couldn't do all 30, but we're going to do as much as we can based on the geometry and the mesh density. And dismiss that. You can see this part is moving, so it's simulating. We're already at 13%. Now I can stop this at any time I want and start it, which is very nice. So if you're at the end of the day and you want to stop your analysis, you shut your laptop, go home and open it back up and restart it, you can do that, which is very nice. So while this is running, I can also go into my results and actually look and see the status. So I don't need to wait till the analysis is finished to get a good idea of what's happening. So I can go back here and turn my geometry on. And then I'm going to go ahead also and turn on my runner, my gate. So we have our feed system there. Let me go ahead and make this window bigger. So first thing I want to do here is I'm going to go to my results and just see, look at my flow pattern here and see what's happening. So already we have a good amount of the part that's been filled. So here if I go to my first time step even, and then we can even advance this. So it's coming through the runner right now, and you can see, it's shooting right through that rib and hitting that boss. So, some slight jetting that's occurring, and it's going to kind of backfill towards the gate and then start filling and so forth. And I can even reload these results. So again, it's running simultaneously, so now we're way up to this point of filling. You can see it filling through the thickness there. And now at this point, like I said, I may not want to let it finish. Maybe at this point I'm not sure about that gate size. I'm not sure about my fill rate. So I want to look and see, do I have too much shear that's happening? So I can go ahead and go right into my shear rate. So okay, well what's my shear? Let's go ahead and reload the latest results. And load my shear rate result and even slice that. So I'm going to slice it in the X direction. Go ahead and slice it apart. And look at that shear through the gate. And make sure we have the latest results. Go ahead here down to, say, this time step. So right now, let me see, shear rate. Okay, so you can see right now, if we're looking at shear rate, we have quite a bit of shear going on through that gate. So go ahead and click on that. So now we can query that value. So now this is only after, let me see if we go down here, after 0.165 seconds. So 33% into our filling phase. And this is what our shear rate is. So go ahead here and see what that value is. So wow, we're already up at 66,000 reciprocal seconds. So we're getting a pretty good amount of shear going on through that gate. So I can go back to my material actually and say, well, what was the max shear rate for that material? So 40,000 is for this material. So I know already that I'm over shearing that material. I'm probably degrading it. So at this point, in reality, what I would do is just go ahead and stop that analysis, go back, maybe open up the gate or slow down my fill time, do something to lower that level of shear that's occurring. But for right now, I'm just going to let it run because the focus today really is on the setup. I just want to kind of show you that. And all right, so we're already at 43% filled. All right, so let me go back to I'm going to open up another interface here. So while that's running in the background, I'm going to bring in another model. So I'm going to create a new project again. And say thermoplastic. We'll call this test 2. Oops. Go into our preprocessor, a brand new window again. Okay, so now I'm going to go ahead and import another model. All right, so here, what I'm going to do is I'm going to bring in this STL file. So it's another housing, but it's a little more complex. So I'm going to use a model here that's got a little bit more complexity to it, some real thin areas. And again, I'm going to go ahead and change that color to something a little more pleasable to the eye. So you can see we have these thin ribs inside there, and down in here some round features and bosses and so forth. Around the edge, you got these thin areas. So this is the geometry that I want to use. And then also, so instead of building my geometry, I want to show the ability to actually import the runner and the sprue. So this was actually created in the CAD system. So I'm going to go ahead and select my runner and my sprue here. Say OK. Okay, so now I've imported that geometry. You can see here now that we have more of this tab fan gate type gate, and then even a shutoff here, something a little more realistic. And the nice thing is I didn't have to model this. It's already in the CAD system, so why model it in the software if you don't have to, right? So at this point, I'm already pretty far ahead. Really all I have to do is put my inlet on. Now the first step here is you see there's these red X's on here. So what I need to do is I need to convert these STLs back to CAD geometry. So I'm going to go down here and say convert to CAD geometry, say yes. Then I really have 3 steps. Put my inlet on, put some sort of steel around it, and then update those booleans, and then I'll be ready to mesh again. So as I did before, I'm going to go ahead and zoom in here on my top of my sprue, specify my inlet, and again, specify some sort of dimension there. I'm just going to stick with my 30 tracer particles, put them in a circular fashion, say OK. Okay, so at this point, zoom back out. Now I can go in and do the same idea as before. Now, you could even go ahead here and put two pieces of steel on. We could put an A half and a B side on here, or we can just do 1 piece of steel. But for today's example, I'm just going to keep it simple and just put 1 piece of steel around it. And it's important to, if you can be realistic, to capture these actual dimensions. So even if you don't know what the mold block's going to be yet, do something that's realistic, because in the calculation, we want to know the distance between that cavity through the steel, because outside of that steel is your ambient air, and the software is considering that. All right, so now that we have some dimensions on here, let's just round these off a little bit. And then here, so make this maybe 80. And then here, what do we have? The Z. Let's just do make that a little bigger, 140. And then I think here we got this probably a little big. We can go down to 15. And then our Y, negative 60. And then our Z, let's do just negative 40. Keep it consistent. All right, so let me go ahead back here to my one view. Let me see here. Okay, so I'm going to go ahead and create my mold again. I want to do this quickly because I want to be able to see through the part now. Because one thing I want to show you is that the one thing we didn't do here is that if you can see, our sprue is inside the steel, and even our inlet's inside the steel. So ideally what we want to do is we want to have that sprue come to the top of that steel, right? Just like you would in the real world. And my inlet, my fictional geometry, I want it to be kind of on top of that. So what I'm going to do is I'm going to show you what I would do, because I'm going to go ahead and hide these. So I don't know the dimension at the top of this sprue, because remember, I didn't create it this time, I imported it. So I'm going to go ahead and zoom in on this. And I really just want to find out in the Y direction, what is that dimension? So let's use my measure tool, go over here and see, okay, so it's 73.520. So we're going to say cancel, zoom back out, and go ahead and turn on my cube and my inlet again. So what I want to do now is I want to modify my cube so that Y dimension is now at 73.520. Say OK. So now if I go ahead and look at this from the side view, I can see that now my sprue comes right up to the top, and then my inlet is on top of that. So this is ideally what we want to do. Okay, so first thing here is I'm going to go ahead and now I want to put these in order again. So we've got my inlet, my sprue, my runner. So in the order again, because again, all this geometry is going to be cut outside of that steel. So when we look at the simulation, we can actually see, that polymer flowing through that open cavity. Go ahead and update my Boolean. Let me go ahead and see what how our analysis is doing over here. So yeah, so we're already at 73% fill, so moving pretty good. I should mention I'm just running this on a dual quad-core laptop that has 8 gigabytes of RAM, so pretty high-powered for a laptop, but not a high-powered workstation. So if I was running analysis on a daily basis, I probably would have some sort of a more powerful workstation. So this still runs pretty nice and fast on just a laptop. Okay, so at this point, we're ready to go in and mesh this part again. So I'm going to go back into my meshing wizard. And all right, so I'm going to start with the automatic. I will say that I typically always use the advanced mode, which I'm going to do next. The automatic is nice sometimes to get an idea, and for simple geometries, it's nice, like I showed you before. But more times than not, the advanced method is what I use, and it gives you a lot more power and control over your mesh. But I just want to show here, if I do the same technique as last time, what happens? Because this one has a little bit more complexity to it. This will probably take a few more seconds just because I do have a full analysis running in the background. So I'm working my computer a little bit. But it's still pretty fast. Okay, so here what we have is, we definitely have a lot more issues now in this part. So we have, 1,300 thin walls, which is one layer, one element through the thickness, 7,000 ones with 2 elements through the thickness. And, and I can even go back up and say bump this up to 5 million. Yeah, so we still have some issues here. So what I want to do is I want to go into the post-processor and see, what's happening. See what that mesh looks like. Where are my, do I need to get a little finer with my mesh? And then I'm going to go through and show you the advanced mode, which is going to give you a lot more ease in meshing. So I can make this gray or white or black. I personally like the white. And I'll go over to my mesh, turn on my grid lines again. Okay, so here I can look at my part. Now I can go ahead and zoom in here and say, okay, well, everything looks pretty good. It's kind of hard to tell with the naked eye, right? So now the good thing is you're not going to have to go in and look and see where those areas are. We have a plot here which is just called mesh quality. So this will show you all the problem areas. So any area in red, so I go ahead and zoom in here. So my areas in red are my thin walls. So you can see we just got one layer through the thickness there. And then my blue are my layers of 2. So any red or blue areas we want to try to get rid of. So I can see here that really those thin ribs are really what's causing the warning. And we want to basically put a better mesh in those areas to capture that geometry more accurately. So I'm going to go back to my meshing wizard now. So instead of using the automatic method, I'm going to use advanced because this gives me a little more control. So if I go in here and click on this, what happens is we get this window. So it's a pretty simple window. You just have a couple parameters. So what we want to do is really assign 5 different things. So in the X, Y, and Z, what I want to do is I want to specify how many elements I want through the thickness. So that's what our accuracy means. So remember I mentioned 3 is what we shoot for. So I'm going to leave these at 3, and I typically would always leave them at 3, unless, again, I have some sort of a really thin wall or high shear sensitive material where I say, you know what, I want to maybe do 4 or 5 to make sure I really capture something that I want more elements with. But 3 for 80 or 90% of the analysis is going to be sufficient. And then my minimum wall thickness. So this is your most important parameter. So when you're in your geometry, what you need to determine is what's the minimum wall thickness in all 3 directions. So what's our minimum in the X, our minimum in the Y, and our minimum in the Z. So I've pre-measured these parts just because I don't want to take the time to tie up here in the webinar. But so my minimum wall thickness in the X direction is actually 3 millimeters. I'm going to specify that as 3. My minimum in the Y was 1.5, and my minimum in the Z was 1.25. Now, minimum element size is just saying, what's the minimum element size for this? So if we're going to do 3 elements through the thickness, and my minimum thickness is 3, so then a minimum of 1. So 3 elements at 1 each, right? 1, 1, 1 would make up that 3. So here we want to divide this, 1.5 divided by 3. So here would be 0.5. So 3 elements at 0.5. And then here, so we take 1.25 divided by 3. Now, I can't do that math right offhand, so I'm going to go ahead here and just bring up my handy calculator. All right, so 0.416. So I'm just going to go ahead and here and say, 0.41. And then these we typically leave at 2 and 5. Sometimes I like to change just to 3. So I'm going to go ahead and leave that at and change that to 3. And just to explain these real quick. So what smoothing is, and I won't get too much into this, is smoothing is determining the ratio from element to adjacent element. So if one element is a certain distance across, the next one's going to be 2 times that. And the one adjacent to that will be 2 times that. And then the ratio is my aspect ratio of my element to itself. So a ratio of 1 would be a perfect cube. Go ahead and say next. Turn off this calculator. Generate. So this should give us a much better idea of the part, because now I've really told the software something about my part. What are my minimum areas, and make sure we capture that. Okay, so a little better, but we still have a few issues. So I still have 574 2-layer elements. So the first thing I want to do is I want to go and I want to see where those are. All right, so let's go ahead and look at this mesh again. Go into my mesh quality. Okay, so if we look at the whole part, we really just have a couple areas. So it's not that many areas that have 2 layers, but it's worth looking at, right? So let me go in here and zoom in. So here we have the blue. We have 2 elements through this geometry, and this is in the Y direction. Y direction here. If I zoom out, go back over here, it looks like the same thing. In the Y direction, I have 2 elements, 2 elements. So and that really is the case throughout the part. I have 2 elements in the Y direction. So what that tells me is I'm going to go back and refine my Y direction parameter just a little bit, see if we can go ahead and put 3 elements through those thicknesses. So I'm going to go back into my meshing, click on that. So in the Y here, so 1.5. So instead of 1.5, let me just say bump that down to 1.2 to be safe. And also pick it because it's easy math, and I can make sure I do 0.4. So 3 elements of 0.4 size would make up that 1.2. Say OK. Next. Let's see if that gets rid of that. Okay, so no errors. So here we have a mesh that's got 975,000 elements. So it's a good amount of elements, but still not unrealistic. It's take a few hours of runtime for something like that. Go ahead and say finish. Now we have a nice mesh on this part. And again, now we're done with the meshing part. And the nice thing about this is we don't have to be, we don't have to go in and clean up the mesh or really, understand how to fix, overlapping elements and moving elements and adjusting aspect ratios and making sure that doesn't affect our geometry quality. And that's really one of the biggest powers of SIGMASOFT is that you don't spend a lot of time on the mesh. I want to focus my time on running iterative analysis. I want to set up, different fill times or different melt temperatures or different insert materials different gate locations and look at the results and see how that impacts things like stresses and warpage and sink marks and weld lines. You know, I can focus all my time on what analysis is really designed for. Okay, so based on that, and we would just go through the same process now. We would go into our definitions now, you know, map that geometry over, and then move on. Now let me go into here. I'm sorry, into the results or into my analysis. So here we're already 97% filled. So this part is almost done with the filling phase. And just, you know, how long has it been? You know, 20 minutes or so. So based on that, I think that concludes kind of what I wanted to show today. Now what I would like to do is go ahead and take some questions. And so in the question box within your GoToWebinar screen, you can go ahead and we can go ahead and take some